Good day and welcome back to Groundwater Quality in Transboundary Aquifers. This is a continuation of Module 2, looking at groundwater quality monitoring. I'm Sumaya Israel from the Earth Science Department in the Western Cape, Cape Town, South Africa. So as I said, we're still busy with Module 2 and we're looking at the development of groundwater quality monitoring programs. This section considers the design of water quality assessment, which variables do we monitor, and which field operations constitute monitoring. So now considering variables, which ones do you monitor? So if we look at the water management cycle, we are now looking at the sample collection, laboratory analysis part of the cycle. Remember our last section ended on looking at the representativeness of your sample quality, and your sample integrity. So some of the very important aspects that you need to consider, we talked about defining your target population and selecting a sample from your target population. So very important is that your target population must be available to be sampled. You could set a target without seeing your study area, you arrive and it's not available. So your target population must be available to be sampled. Your samples need to be randomly collected without systematic bias. You also need to use procedures and sampling devices that prevent segregation and minimize your sample variation. For example, a specific depth sampler to get a sample at a specific depth in a borehole, maybe where the screen sits. Determining your sample representativeness involves careful planning and formulating a proper sample design or sampling design. It can't be determined by statistical analysis after the fact. Like you can't collect samples and then determine later if it was representative. It's something you need to do before you go out or before you sample. You must have flexibility to document compromises during your sampling. It's very important to document everything you do during your sampling so that you can pick up whether you've done anything incorrectly, for example. How many samples? This is a tricky question. There's no cookbook or defined approach, and it's more of an iterative process or approach. What you do need to take into account when deciding on your samples is heterogeneity in terms of distribution, in terms of composition, in terms of morphology. So remember in the earlier or the previous presentation, we talked about the geology that can be variable. We talked about the hydrology, the geochemistry. So all of those variables need to be taken into account when you are deciding on your number of samples. Sampling frequency and adequacy. Your final sampling frequency is normally determined based on variability of your critical parameters, your prediction objective, and your required accuracy. Your critical parameters may be those that you want to assess to understand a system, a specific parameter. If you are looking at iron, for example, you would consider whatever information you have for iron, and how variable it is in your environment that you are sampling in to decide on your frequency for that particular parameter or your frequency for your monitoring. So in essence, your adequacy of sampling must be tailored to the site condition. If you were sampling in an area where you might have acid mine drainage, you might sample for iron quite frequently, as it's an environment where the concentrations can vary and can be high and vary quite quickly depending on changes or flow or interaction with oxygen, for example. So some more monitoring and sampling considerations. The sampler going out to collect the sample needs to decide if a single time and location meets the needs of the investigation. So these need to be linked closely to your objectives. And your objective might define this for you as well. Can the water be assessed by an averaged value with time and location? Do critical minima and maxima require individual measurements? Your collection procedure needs to be, is it correct? Is it the correct weighing of individual sampling done to cover your temporal and spatial variation? So all of these need to be considered by your sampler out in the field. Then very importantly, the behavior of species to be sampled. I use an example here of redox sensitive species. So if you are sampling for heavy metals or trace metals, filtering, acidification could be needed for preservation of your sample or to ensure that your data that you collect is valid. You should not be sampling unused boreholes, but sampling in unused boreholes relates to stagnant water. You should be taking field duplicates, 1 duplicate for every 10 samples. Lab duplicates are very important. Also, in the laboratory, instrument duplicates are also important. When you are sampling for hydrocarbons, for example, you would need to use low flow sampling. In fact, if it's heavy and light non-aqueous phase liquids, you would use different sampling techniques. So the person sampling also needs to have an understanding of the chemical behavior of the species to be analyzed. Some examples of these, where you have hydrocarbon polluted areas, you need to know that samples have both the gaseous and aqueous phases. And this refers to areas like refineries or areas around refineries. When you have heavy metal contaminated areas, example the mining areas, you have redox sensitive species, you could have suspension sensitive species and pH sensitive species. In agricultural areas, you may have phosphate and nitrate, some pesticides, herbicides, and fungicides. And when you're looking at municipal waste, you have to consider pharmaceuticals, cosmetics, detergents, and organic pollutants. So all of these need to be taken into account when you are sampling, also when you are developing your monitoring network, all of these land use activities or potentially polluting activities in a particular area. When we consider processes, chemical processes, a process like sorption has control over the fate of many trace elements in natural systems. So as an example here, sorption of metals onto suspended iron and aluminium-rich particles is a predictable function of the metal itself, where you have metal concentration, pH, amount or the type of suspended particles and temperature all playing a role in the reactions that take place. Now, if we consider pristine sedimentary basins, remember we are still looking here at which parameters to monitor and how frequently, and some characteristics of your study areas that may help you define your objectives and your parameters and your sampling frequency. So if we have a pristine sedimentary basin, you would find some characteristic chemical compositions depending on where you are in this basin. And one could say that the groundwater composition changes progressively along the flow path, with your fresh recharge being in the higher lying part of the catchment, for example. And this would be a carbonate rich, mostly calcium carbonate, which might change to, which might be calcium and or magnesium carbonates. When you get to the middle section of the basin, you might have more moving towards sulfate rich or bicarbonate sulfate, and then dominated by sulfate bicarbonate. And as you move closer to the discharge zone, you would find sulfate and chloride being dominant, with our coastal or our areas that are further along the flow path being more chloride rich. With these chemical changes, you also have a decrease in redox potential and flow rate. So in essence, when we have a big sedimentary basin, there's also an increase in age and residence time, which relates to longer water-rock interaction, some ion exchange processes. So you'd find younger water in your recharge zone, and you'll find much older, more salt-rich or dissolved salt-rich in your discharge zone. So these also need to be taken into consideration when you are setting up your monitoring network. In terms of temporal and spatial scales, we can see here that different processes occur at different scales, both temporally and spatially. And the diagrams on the left show the different scales of the different processes. These also need to be taken into account. It's your geochemical processes and the duration of those processes. How can we tell what the quality of groundwater is at a specific area, and how would we understand what is happening in a particular system? Typically, we can monitor indicator parameters, which we can measure and and help us understand some of our groundwater systems. This can be measured easily with our handheld field meters, and they are normally the first indication of what may be happening in your groundwater system. Of course, this would be first indication, and laboratory analyses will follow the field measurements. So some of these parameters that you can measure in the field include your EC, pH, total dissolved solids, temperature, dissolved oxygen, redox potential, and your turbidity. So these indicators give you, well, it's indicators. So it can give you an idea of if you were in a sedimentary basin, for example, where about you are, you're looking at your dissolved oxygen, looking at your total dissolved solids, your pH and EC. They can also give you an indication of pollution. They can also give you an indication of fresh recharge. So this would really be your first indication of what's happening. You can add to that alkalinity, hardness, dissolved organic carbon, and isotopes, and these relate to other processes that can help you understand what's happening. An example of a mining area. We know that aqueous metal concentrations are highly variable in mining areas, and it normally depends on the location in the catchment. So where are you with respect to maybe the source? What is the underlying geology? How weathered the ore deposits or wastes are? The climate in your area, and then also the dominant geochemical processes. These processes or these metal concentrations can vary seasonally, daily, even weekly, and are impacted by stream flow or storm events. In conclusion, chemical species behavior, for example, redox sensitive species, need to be taken into account. Land use activities and the potential impacts of pollutants need to be taken into account. Once you know the species behavior, or you've identified the likely species in your area based on land use or your natural systems, daily, monthly, seasonal, and annual changes need to be considered. Also, the temporal and spatial distribution of processes and activities need to be considered when selecting your sampling frequency and your parameters. Thank you. I hope that you've taken in some information during this talk.